So I'm outside the field that is essentially discussed in your circles, but I wanted to introduce to you the notion of what you all know, the ROS, the reactive oxygen species, as being an important player in many questions relating also health and well-being of people. So I titled my presentation as "Why do we breathe oxygen and what is ROS?" How do I get to the next?
Yeah, why is it doing that?
Next
slide.
slide.
Should be okay.
Yes, there it is. So today I would like to talk about a reactive oxygen species with which you certainly are all very familiar, and also a little bit about superoxide dismutase as an enzyme that plays an important role in this. And why? Well, the field of radicals biology began around the end of the 60s with the discovery of superoxide dismutase, SOD, which is a structurally complex enzyme. For me, as a non-biologist, non-medical person, I'm amazed how complex this SOD is structurally. And it's supposed to be a very ancient enzyme, and its main function is to fight the reactive oxygen species. Now, at the same time, and I think is a link to the topic of this meeting here, the ROS are at the root of many problems with living organisms, including diseases and illnesses. And the reason is that probably even the earliest living organisms, 2.4 billion years ago and longer, already had to defend themselves against the effect of reactive oxygen species present in their environment. So my main goal is to convince you that ROS is something that is part of our natural environment, and that ROS existed since the beginning of the Earth. And one example how to explain this is to address the question how the Earth acquired an oxygen-rich atmosphere. Now, there was, and still is, a widely promoted and widely accepted idea that very early cyanobacteria invented, out of the blue, oxygenic photosynthesis and started to pump oxygen into the Earth's atmosphere. And this is how the Earth became oxidized, and how eventually our atmosphere acquired a 20+% percentage of oxygen gas. Now, the question that surely comes to everybody's mind is, why would cyanobacteria produce a gas like oxygen that is highly toxic, lethal to them, and to any other form of primitive life, meaning life that has adapted, created in and adapted to a pervasively reducing atmosphere where oxygen was not present. And the only logical explanation is that reactive oxygen species were already present in Earth's earliest environment and needed to be dealt with in order to even develop life. And therefore, ROS predate life. So then the question rises, what actually is ROS from a geophysics, geology viewpoint? And here I need to introduce the word peroxy, which, if you look it up in the dictionary, you'll find it in the chemical dictionary. But if you look at the geoscience or geobiology dictionaries, the word peroxy is absent. However, all rocks in the Earth crystallize in the presence of water, and hence, when something crystallizes in the presence of a reactive gas like water, traces of this gas dissolves in the structure of these minerals. And here is a short presentation on the path towards peroxy in nature. On the left at the bottom in red, you see a section of a typical mineral, let's say a feldspar that makes up 60–80% of the rocks of the Earth's crust. It's formed by SiO4 tetrahedra linked through single oxygen bonds. Single oxygen bonds. Now, when these minerals crystallize, they always do it on Earth in the presence of water, and therefore water reacts with this bond and breaks up the SiO-Si bond and inserts itself in form of a pair of hydroxyls. And there is an important but little known redox reaction that takes place inside the Earth, namely that this pair of hydroxyls that you see here in the middle on the left side can undergo and do undergo an interesting redox conversion, namely that the protons of these two OHs steal an electron from the oxygen in which they are embedded as part of their being a hydroxyl. They form molecular hydrogen, and the oxygen is oxidized from the O2 minus to the O single minus state, forming a peroxy. Now, this is a process that happens inside the crystals, but it happens also to a large extent along grain boundaries of the rocks that form the Earth's crust. Therefore, peroxy defects form the link between the minerals, and that has an important consequence, namely when this bond is stressed. So here you have again the kind of peroxies everywhere, but peroxy are mostly found along grain boundaries linking mineral grains. And now if we have seismic processes, and there comes my basic work on related to earthquake, understanding signals that the Earth produced prior to earthquake, then rocks are deformed, and these peroxy bonds sitting on the surfaces of mineral grains, when the mineral grains are shifted, these bonds on the atomic level are stressed, are bent, and you can show, we have shown that this causes a shift in the electronic structure of this SiO bond and leads to a transfer of an electron from an outside oxygen double minus into this bent SiO bond, and the outside oxygen double minus has donated the electron, becomes an ROS, a reactive oxygen species. Now, this is not a species in a molecular sense. It is a charged state in the solid state, and it is characterized by a number of interesting phenomena, including a delocalized wave function, and that is beyond the goal of this talk. But peroxy are everywhere. And therefore, if peroxy are everywhere in the Earth's crust, ROS are also everywhere, because as the Earth's crust undergoes deformation by tectonic forces, by the tidal forces, and tectonic forces, for instance, prior to earthquakes, that's the opportunity for us to study them more precisely, we see the effect of ROS. Therefore, ROS, reactive oxygen species, have been around since the dawn of time, long before the advent of life, and long before any advanced forms of life existed on Earth. So ROS are very, very primitive in the historical sense of life. Now, if these peroxy bonds exist in the rocks, and rocks are weathering, and I remind you that still today, every year we just measure the amount of water coming down the rivers and measure the dissolved silicates in these river waters. We know that about 3 cubic kilometers of rocks are weathering every year. And in past times, it was probably more like 10, maybe 20 cubic kilometers. And we know that these peroxy are present in average rocks like granite and basalt. It's a concentration range of somewhere between 500 and maybe 2,000, 5,000 parts per million. You can calculate how much oxygen would be released during weathering, and it's substantial. There is no need for early microbial entities like cyanobacteria to have invented out of nowhere oxygenic photosynthesis to produce oxygen to be injected into the Earth's crust. This formation of oxygen was a natural, geological process that actually caused the earliest microbes. In order to survive, they needed to defend themselves against ROS. It's not the other way around like it is presented in many textbooks, even in textbooks that are taught in school. That's some information that I got from my friend Victor Stolz. His son is in high school, last year in high school. And he said, yeah, we learned about it in school. Cyanobacteria produce the oxygen in our atmosphere. No, it's not. So I'm coming to a quick summary here, saying that peroxy is still widely ignored in mainstream science and geoscience and in biology. But peroxy has played a major role in the evolution of life and evolution of Earth, including the Earth's atmosphere. And therefore, understanding peroxy helps us understand many aspects of our home planet that are still poorly understood, including why do we have an oxygenated atmosphere? And also, I may add, why Mars is red and highly oxidized. And one could probably save a new $1 billion to convince NASA that one of the motivation to go to send astronauts to Mars, if it is to look for life on Mars, you don't need it. The Mars has been oxidized, not by microbial activity, but it has been oxidized by processes that are inorganic in nature. So this is what I wanted to contribute to your interesting gathering, and I'm sitting here and I've been sitting and listening. And really, I think peroxy is something that we need to understand better in order to understand the Earth itself and to understand the early formation of life and why we have an oxygenated atmosphere. Thank you.